All right, let's get started. So welcome to the last week. So today we will continue with the topics of minimum spanning trees. You have started the last lectures, and before we really go to the new topics, maybe let me just have like a brief recap about what I have talked about, what type of materials and the topics we have covered in the last lectures. Right. So last lecture, we'll talk about the, like a minimum spanning trees. We started with some background introductions about the minimum spanning trees, like also talking about some, several main properties of minimum spanning trees, like no cycle properties, like if we cut the minimum spanning trees, the remaining two pieces are also minimum spanning trees. Then we're talking about two useful property, no cycle property, sorry, cycle property, which means that like largest weight across the cycle is always not in the minimum spanning trees. And someone sign on showing up in the room. Are we all good? Okay. Um, our student on Zoom can see the screens. Can anyone give me the answer? Okay, great, thanks. Okay, then we'll talk about the cut properties, which means the minimum wage across the cut is always in the minimum spanning trees. All right. Then we're talking about like how to generate this minimum spanning tree out of the graph. We're talking about the generic minimum spanning tree algorithm with like red rules and blue rules. So we keep applying this red rule and blue rules, and we will onto the arbitrary edges. Then we will, the result will be the, like a minimum spanning trees, and then we enter these principles of the generic minimum spanning tree algorithms. We also dive deeper into two famous algorithms, like a Prime's algorithm and then Kraskow's algorithms to generate the minimum spanning trees outside of the graph. And then we move on to talking about some variations, right? And we talk about variations. We first topic would be like a constant weight edges and like a bounded integer weight edges. Then we're starting to talking about minimum spanning trees on directed graphs. Remember, like at the very beginning of the last lecture, we just say like, okay, the materials we're talking about is applied on weighted graphs, weighted undirected graph. Okay, let's move on to the directed graph. What would happen if we apply minimum spanning trees on directed graphs, right? So we're talking about the minimum, like a directed minimum spanning trees, though the problem definition become really hard. If the edges are directed, it's hard to define what would be the minimum spanning trees, right? And you probably want to know there's one specific, one of the formulation would be, so we just have choose the root. And then we kind of generate like a spanning tree so that like every node is reachable. There's the path, thus every node is reachable from the path to the from the node of the root to the node, right? There's no cycles in the process. And then it turned out that it would be like extremely difficult problems since all the properties are gone. The cut properties are gone. The cycle properties does not hold. The generic minimum spanning tree algorithm does not work at all. Then this the result would be like a primes, Kraskow's, and this hyper algorithm only works, right? But the good news about this specific cases is there's a specific case. For example, like a directed cycle graph with one node, with one root. In these cases, it turned out that we could have a relatively like a simple algorithm to generate these minimum spanning trees. All right. The main procedure would be like for every of the nodes except the root nodes, we just add the minimum weight incoming edges. I mean, that's it. After adding this procedure, after just generating these procedures, we will have like minimum spanning trees, right? Directing minimum spanning trees for these specific cases, right? Why this is the cases? So we consider with some of the observations. Okay, maybe let's see what I can uh, stop sharing this. A little bit annoying with the top on this one. Okay. Let's see, I can get rid of. No, cannot. Right. Let's move on. Why this would be like a simple cases to generate the minimum spanning trees. So there are several observations that will help us to draw the conclusions. First of all, there's no cycles, since our definition about this is directly a cyclic graph, right? And then we will have like a V nodes. And by applying these algorithms that we have talked about, like every node except the root node as the minimum incoming edges, we will definitely have V minus 1 edges, right? And this would mean that this will be a tree. And also there will be no cycles. So we have a V node with V minus edges. There's no cycles. This would indicate that it would be a tree, right? And also, when we build these trees, we actually choose the minimum incoming wedges for each of the nodes, right? So this would lead to the result that this would be the minimum spanning trees, okay? And that will be the relatively straightforward one. And the conclusion is for these specific cases for directed a cyclic graph with one root, we will be able to generate this minimum, like directed minimum spanning trees in OE times, right? And that would be like a simple specific case. I mean, it only works in the specific cases. Now let's move on to another topic, which is like a maximum spanning trees, right? When talking about the minimum spanning trees, the definition of minimum spanning tree is it is the spanning trees of maximum weights. And how do you find the maximum spanning trees? So before we really answer that questions, let's consider this like a related questions. So what would happen if we reweighting a spanning tree? What would happen if we add like a constant k to the weight of every edges, right? Would this have a huge impact on the final result? It turned out that it really does not matter. We can go through the Kruskal algorithm to test this conclusions, right? If we look at Kruskal algorithm, the basic idea would be we are going to sort the edges by weights, right? And then we'll consider the edges in the ascending orders. If both ending point of the edge is in the blue trees, we just color the edge red. Otherwise, we color the edge blue, right? If we go through these procedures, you will realize only relative weight matters, right? The absolute weight edges has no impact at all. And then this would consider when we consider this generic minimum spanning trees, we have red rule and blue rules. And we will be able to draw the conclusion, say if we add a constant k to the weights of every edges, there's no change at all. We will directly have the same result of the minimum spanning trees, right? Which means that we can definitely add or subtract the weights without affecting the minimum spanning tree. However, this would be very different from the shortest path. I think we already covered this, or you can think about after the classes, why this is the reason. All right. And then after we have this one conclusion, say we can directly add a constant values to every edge of the tree without affecting the results. Maybe we can looking back to see what would be the problems with negative weights, right? How we're going to dealing with minimum spanning, the problem generating minimum spanning trees with negative weights. I mean, one straightforward to apply these ideas would be we just add a relatively big enough values to each of the edges. So that is positive. Then we directly apply these minimum spanning trees, right? But we really do not need to go that far. Actually, there's even no need to reweight, right? Since we have talking about in a few slides before, only relative edge weights matters, right? So negative weights has no bad impact at all. And after we're talking about this a few topics, we have talking about how we are going to dealing with reweightings and negative weights. Now let's touch the topic or the problems of how do you find the maximum spanning trees, right? It turned out that the procedure would be relatively easy. We just multiply the edge weights by -1, then we run minimum spanning tree algorithms. And the result of the minimum spanning tree will give us the most negative minimum spanning tree, right? And we just flip them back, it will be the maximum. By doing this, we're able to generate this maximum spanning trees out of a graph, right? And that would be the topics about maximum spanning trees, right? With this, we have just finished all the topics and the materials about the minimum spanning trees. And then let's move on. Let's take like one step back. Let's consider like, okay, what would be the next main topics, which is dynamic programming. But really before we talking about dynamic programming, though, we will have like overview of the semester roadmaps. Since this will be the last week of this whole semesters, right? I mean, we will have like a brief recap or talking about what's exactly topic we have covered so far, right? We started with the searchings and sortings when we're talking about like a list and a trees, and also spend time talking about like, like hash tables and graphs. Then we will talking about the last topic, which is dynamic programming, which we will wrap up the whole semester, right? And so the roadmap for today and Wednesday's lecture is all about the dynamic programming. So we will start with some basic introduction about like dynamic programming, the basic ideas and principles and background of dynamic programming. Then we will help you to guide through the main ideas of the dynamic programming so that you could, once you grab it, digest it, you should be able to apply the ideas of dynamic programs to a wide range of like problems, right? And definitely we will walk you through several examples of the problems. We will start with the like easiest one, which is the longest increase in subsequences. And we'll continue with like a bounded price collection and a vertex cover on the trees, and so on, right? I don't think we have enough time to cover, like all the materials. So we'll just continue and resume the topics on Wednesday, all right? So first, we were talking about like the dynamic programming. So there are always like key factors about this. Sorry about this. Maybe just let me pause for a while. I really find it annoying. Let me see whether I can get rid of this, like these titles. Okay, great. So there will be like one of as I mentioned, like there will be like two key features or like principles or ideas behind of this dynamic programming. The very first one would be called like optimal substructures, right? By talking about optimal substructures, we are talking about like you're able to, when you are dealing with one specific problems, you will be able to divide these big problems into smaller pieces and smaller problems. And then you're able to solve these smaller problems optimally. And you will be able somehow to combine these results or the solution, optimal solutions of these small problems and combine them to solve, like the original big problems. In other words, the, like the solutions to the bigger problems depends on the solution of smaller problems, right? I mean, this would be like optimal substructures. Then let's move on to like questions. So which can you answer like which of the following problems would exhibit optimal substructures, right? You can choose all that apply. Let's consider like these cases. We have sortings, we have reversing of screens, merging two arrays, shortest path, and minimum spanning trees. All right, which of these problems exhibits optimal substructures? All right, it turns out, like all of this actually exhibits optimal like substructures. I mean, sortings, like it's a classic example of divide and conquer algorithms where you're able to, like if you're able, it is nice to sort these arrays if you're able to like divide it into two half of the arrays with the sorted one, right? And the reversing screen is also like examples optimal to exhibit optimal substructures. Merging two arrays is also like a classic way of like a divide and conquers. And for the shortest path, it is also the same things. Like the shortest path from like a position A to position B consists of like a shortest path is of all the items along that way. right? A smaller problem of shortest path along that way. For the minimum spanning trees, we have just talked about this like topics, like in the last lectures. It already exhibits optimal substructures. So so this kind of optimal substructures is like it exists in like almost like all these problems, especially we're talking about like greedy structures or greedy algorithms or divide conquer algorithms, right? And we can take like a merge sort examples. So merge sort is definitely like dividing the conquer algorithms. Like we are able to divide the arrays into two halves, then are able to have a way to sort these two arrays, and they are going to merge them back. So this would be examples of like divide and conquer, and also be exhibits this optimal like substructures. All right. And if we look at so these ways, maybe we will have like a pictorial representation. We will talk what exactly what we're talking about of like optimal substructures. We can consider like we are trying to solve like a big problem starting at here. And then we are able to like divide this big problem into smaller problems. We'll keep the dividing this until that we reach this very end of this like lines. So we have a bunch of smaller problems of which we will be able to finally solve, right? Once we will be able to solve this optimally, we will combine them back to solve these original problems, right? This would be like optimal substructures. Remember, like I said before, there will be two things behind or related key things or features related with dynamic programming. One would be optimal substructures. The other way would call like overlapping subproblems, all right? When we're talking about like overlapping subproblems, which means that like after we divide this big problem into smaller problems, we will realize that the smaller problems is always like is used to solve or multiple different bigger problems. Or in other words, these smaller problems are shared by like different bigger problems. If we talk as these specific cases, like if you look at these examples, you will see like you see shared or by these two like bigger problems, right? There's like a dependencies here, and these are reflects this like overlapping subproblems. And this would be like one of the pictorial representations, like overlapping subproblems actually is very important. It makes this like a dynamic programming challenge and also interesting because it requires you to identify what exactly is the overlapping subproblems, right? And sometimes the overlapping subproblem structures or dependencies may be simple, as we see in the previous slides. But some cases it can become extremely difficult, like in these cases. One you can see like one small problem is shared by like quite a few of like bigger problems, all right? And so this is like a pictorial representations about these overlapping subproblems. If we compare, like the dynamic programming with like dividing the conquers, you will see they share some differences and also similarities, right? The similarity would be like, like both of them contains like optimal substructures, which means that we are able to divide the big problem into smaller pieces and trying to solve these smaller pieces, and we are able to combine this answer to the small pieces and getting back to solve these big problems, right? However, the difference is between like dynamic programming and the divide conquer is for dynamic programming, we will have like like this overlapping subproblems. So in order to solve these bigger problems, you probably each of the small problems actually are like shared by like quite a few upper problems, right? And this would be like a comparison between dynamic programming and also divide conquers, right? And then after this introduction about this like two key things that you need to aware about the dynamic programming, you're probably already interested in, okay, how we are going to solve this dynamic programming problems, all right? So the basic strategies are what we would be called like a bottom-up dynamic programming. The idea will be at the very first step, we are going to solve these smaller problems. So after this kind of divided problems into big problems into smaller problems, we keep the dividing this until they are at the very end. So that when we're talking about this like a smaller problem as the bottoms, it looks like we are able to solve these smallest problems since there's no dependencies at all. And we are able to derive their optimal solutions, all right? And once that is done, we are able to combine these answers to the smallest problems to solve like problem as the next levels. All right, we keep doing this, keep doing this until we're able to solve this like root problems. So this is what we call the bottom-up dynamic programming, which means that you start with the smallest problems and you gradually build up the solutions to the root problems. All right, this will be the ideas. And then, like before we really talking about this like a bottom up or like problems when we talking about, when we look at the dynamic programming from another point of view. All right. You can consider like this or like, we can consider like dependencies as like kind of edges, all right, direct edges. And this kind of remind you about, this may sound like familiar to you, right? I mean, this is kind of related with directed cycle graphs. We have schedulings and, like we have a topological sorts, right? And if we are kind of say like want to like order this task in a way so that all the dependencies make sense in the directions, right? And after that is done, we are first step we do would be we are going to apply this topological sort of this directed cyclic graph. And after that is there, we're able to solve this smallest problem in the reverse order one by one, right? And that will be like the source. So like today we're talking about the dynamic programming, right? But like if you're already familiar with this DAG and the like, topologic source, which means that you probably already be able to solve these problems without even knowing this is dynamic programming, right? And also you probably want to answer is ask is, okay, this kind of have a like specific requirement, saying like there will be like no cycles, right? If we have this kind of dependency, we represent the dependency as a direct edges, whether there will be chance of the cycles. Turn out this answer is no, right? I mean, if there's the cycles in the divided, when we divide this problem into smaller problems, there's no way that you will be able to solve this, right? This kind of guarantee that there will be no cycles in the dependencies. Okay, this would be like a second point of view of talking about how to solve this dynamic programming. The next one would be like called like a top-down dynamic programming. All right, top-down dynamic programming is related with the word of recursion. Like you start as the root problems, you do recurse the problems. You keep doing this multiple times until you realize, okay, at a specific point, we are able to solve the problem now. All right, we keep doing this as the very bottom lines. We have a bunch of problems we could solve. And once that is there, we're able to, like combine the solutions of the smallest problems and gradually back to solve this problem at the next levels and keep doing this. And one thing to notice is like always, like the overlapping like properties, right? Which means that in the process, we probably you probably want to like have a way to memorize, the results, so that you only need to compute like each solution once. Remember, like in the process, it will be like overlapping problems. We solve this higher level, this higher task, we will require, like this task if we study multiple times. Okay. It is common mistakes that if you keep solving the same problem duplicate times, multiple times, right? So make sure that you should have a way to like derive the optimal results and only compute the solution once, right? That would be the one thing to notice. And like if you look at like like classic textbooks, we always like introduce the problems of like we are able to solve like divide this dynamic problem into several set of subproblems. All right, they will show like a table views. Like this would be like classical ways to describe this. And each items in this like tables would be like one subproblems or small subproblems. There will also be some like dependencies of these nodes. All right. The disadvantage of this table view is always like does not provide you with the viewpoint of the dependency. Okay, which is super important, right? But still, table view is a good way to visualize this and talking about the subproblems. Okay, so we have talking about now, like the basic, the two key features of this dynamic programming and three different views to look at this dynamic programming. So we know like the differences between divide and conquers and dynamic programming is dynamic programs have overlapping subproblems, while like a divide and conquer has no such things. So do we have any questions so far? Are we all good about this? Okay. Then we will move on to talk about, more specific problems. We are going to apply these ideas of dynamic programming to solve a bunch of example problems. So we will start with one of the easiest one, which is called the longest increasing subsequences. All right. So longest subsequence, like the longest increase in subsequences will be like the problem formulation is look like this. So the input will be like a sequence of integers. For example, in this case, we will have like a sequence of, like 7 integers with 8, 3, 6, 4, 5, 7, 7, right? The output of the problem is we are hoping that you can come out with like an increase in subsequences, right? From this input sequences of integers. For example, in this case, one example of the output would be, we would have like subsequences of 4, 5, 7. We highlight in red colors. Okay, these are like indexes of the like increasing subsequences. You can see like 4, if we're going 5 and 7, they are going to increase one by one. All right. And the goal for the longest increasing subsequence is you want to output, like a sequence with the maximum length. All right. The result would be, one of the possible results would be like a 3, 4, 5, and 7. All right. We highlight in these colors here. These are just reflecting you that like the consequence, consecutive is not important. As long as you have like subsequences that are increasing one by one all the way. All right. So that would be the expected outcomes of these problems. But before we really, directly solve this, let's make these problems easier, make our life easier, simpler. Okay. Instead of directly output the increased subsequences, we just ask you, we make the problem simpler. We say like, you only need to tell me the length of the increasing subsequences. All right. In these cases, the examples of the previous subsequences would be 3. And the maximum length of the increasing subsequences of this particular cases would be 4, right? I mean, this would be like what we want. And how we are going to tackle this. So you probably be able to already consider this in like a directed acyclic graph. You want to modeling this as like a directed acyclic graph, right? So we start with the node 8, and like it will be if you find out, okay, there will be like an increased numbers from A to B, we just draw the index. We just draw like directed edges, right? Let's start with the node 8. Unfortunately, node 8, there will be no coming edges since 8 is almost the largest one in the arrays. So let's move on to slide 3. So, there will be like outcoming edges from node 3 to node 6, 4, 5, 7, and 7, right? I mean, these are like the nodes that are bigger than node 3. Let's move on to the node 6. There will be 2 outcoming edges from the node 6 to 7, 7, which is last 2 nodes in these areas. All right. We keep building this like a graph, like from node 4, it will be like I think it will be 3 edges from the node 4. That's pointing from 4 to 5, 7, 7. And from the node 5, there will be like 2 outcoming edges pointing to both 7s, right? I mean, this would be the modeling of the directed cyclic graphs, right? So you remember, like when we're talking about this, we look at this from DAG solutions or DAG directions to formulate this dynamic programming. So to think about these problems, the very first thing is we need to do is do like a topological sort, right? This is not nice. After building these graphs, really this is already there. We do not need to do nothing, right? And then the second step would be we want to calculate in the longest passes, right? I mean, that would be the a requirement of these problems. So we just consider like a longest path finding problem to be the black box. We directly apply this on node 8. And the result will be like 0. I mean, 8 is largest one. There's no edges coming from like node 8. Okay, we just treat this finding longest path as a black box. We continue applying to the node 3. Then we'll realize we have like a length of 3, right? And we keep applying this to all these nodes. You will see like the longest path starting from node 6 will be 1. Like the longest path LP4 would be equal to 2, right? And the very last twos would be LP7 would be 0 and 0, right? And after we have like a longest path for each of the nodes, we will be able to like calculating the longest path. We just pick up, okay, what would be the longest path throughout the whole graph. And after we identify the longest path, we're going to have just add 1 on top of this. This would be directly the length of the longest increasing subsequences, right? Why we need to add 1? Because like the longest path just counting the edges, right? And we are required, we actually counting on the nodes. So that would be like a maximum longest path plus 1. There will be like a length of the longest increasing subsequences, right? And that would be the whole procedures of using this like a DAG algorithm to solve these sequences with n numbers, right? So after this is after we describe these procedures to finish the jobs, I guess it is time for you to consider or to evaluate whether this is efficient grid algorithms, what will be the running times of the DAG algorithm for subsequence of n numbers, right? I just gave you like a few more seconds to consider what will be the results. I have ON or ON n log n or ON square or n cubic. Right? Let me see. Okay. The result actually is n cubic, right? Why? Maybe let's consider, let's have like a detailed analysis of the DAG algorithm we have worked out together, all right? So if we consider like longest path, like the complexity, the running time of the longest path finding algorithm would be like the order of vertex and edges, which would be like O(n) squares. And we are going to apply this longest path finding algorithm on each of the nodes, right? And it means that we are going to repeat this. We are going to run this longest path finding algorithm n times, right? And this will give us the result of n cubic. I guess after you saw these algorithms, you already starting to consider, okay, this whether we can do better. This seems like silly to do this, since we are keep applying this longest finding algorithm like multiple times, like without saving like all this any intermediate results, right? Because you can consider like finding the longest path of like a node starting from node 3 is already related with finding the longest path from node 6, right? And what would be the better way to do this? So you probably already realized that we need to consider like the overlapping style problems. Like we probably want to start, since there's this kind of properties, we probably want to start with the smallest style problems, right? Which is LP7. Like LP7 is the smallest one. It only have one node. It does not have any edges. All right. Immediately we know the LP7 equals to 0. Right. And then we can continue applying to the second last node 7. Again, it will be just the isolated node with no edges. The length of this node would be the longest path starting from this node would just be 0. Right. And then we kind of we already know the result of this smallest problem. Let's continue going on to grow this make it a problem on the next levels. Right. Let's consider LP5. We're talking about LP5s. How we are going to do this? How we're going to do calculating this? We like one direct way to thinking about this is we're going to calculating like the maximum outcoming edges from node 5. All right. And there will be just the 2 edges coming outside of node 5s. And we already know the result of the longer LP, like the result of LP on the other side of the 2 nodes. Right? And what we need to do is just finding the maximum values and just add one of this, right? The maximum between LP7, LP7 just 0, we just add 1, will give us LP5. LP5 equal to 1, right? Then these are the kind of ideas. Let's continue how to calculate LP4. All right, we keep utilizing these overlapping subproblem properties, and we're calculating examining each outcoming edges from the node 4. Then there will be 3 outcoming edges from node 5. For each of the node on the other side of the edges, we already know the results of the longest path starting from the specific node, right? And what we're going to do is going to take the maximum between this LP of these 3 nodes. Then we just add 1 on top of this. This gives us the result of LP4, right? Which is 2. I guess you already get the main ideas. Now let's consider how to derive this LP3. LP6. LP6 would be 2 outcoming edges. Again, we find the maximum result from the rest 2 nodes and just add 1, right? Then we could do this, keep doing this until we do this to LP3. Again, we find the maximum outcoming edges, and we calculating LP6, LP5. We already solved LP6, LP4, LP5, and etc. So LP3 just take the maximum result, maximum values among all these LP nodes and add 1 on both of this, and this will give us LP3. All right. So this would be the general procedures of how to solve this, right? And if we look at this longest increasing subsequences we are going to talking about, we are going to summarize and have a relative abstract way to describe the ideas, right? Assume that the input will be arrays with a node of an index of n from index 1 to n, right? It will be very crucial to define the subproblems, right? In these cases, we can define this subproblems of Si to be longest increasing subsequences from the index 1 to from index I to n. It's we are going to calculating the longest path starting as the index I, right? One example, this will be the one of the subproblems. For example, we have the input sequences of 7s. It's just same a sequence of integers in the previous slides, and we're calculating S5. All right, the S5 would be the longest increase in subsequences start from index 5. Right? If we start from index 5, the length would be 2. All right, you can see we're starting from the index 5. Then this will consider these 3 cases, right? And the longest one will be 2. And S2, in these cases, S2 would be, the result would be 4, right? We're starting from the index 2 and calculating the longest path, longest increasing path from these indexes until to the very end. This would be the definition of the, subproblems. And, this would be great if we look at these table views. So each of the node would be reflect the definitions of subproblems, right? We have a nodes. We have different nodes from 7, 7, 5, 4, 6, 3, and 8. Okay. The subproblem would be finding the longest path that is starting at node X. I mean, from the spawn is the problems the node starting from the length starting from node 7 is already 0, 0. We just put these results, right? I mean, this will be a table views of look at the subproblems. And again, how we are going to, after that we have identified the, a definition of the subproblems, we will be able to, describe how we're going to solve this, the results or solve this problem using subproblems, all right? The very first step you want to do is always look at the smallest problems after these subproblem definitions. The smallest problem would be what would be the result of Sn, right? Sn would be the very last one. So there's no edges come outside of the edges, so definitely the result will be n. Immediately we can solve this smallest problem immediately. And then we will need to consider what would be the result of Si, right? The definition of SI is the longest problem starting from index AI, right? And then to calculating this, we probably want to look at, like all the outcoming edges from the node I to node J, right? Remember, when we're talking about SI, we already solved the result. We already have the result of Sj. What we need to do is we're calculating all the outcoming edges from node I. And once we identify the node of the other side of the edges would be Sj, we just take the maximum of all the possible nodes that are connected to the node I with the outcoming edges from I to J. Right? After that, we just have one index number. We just add one on top of the maximum result. And with this, we were able to solve this problem using these star problems. All right. And you can keep considering this. These are actually illustrations of the, like the problem, how we're going to solve the problem using the star problems. All right. Like after the like relationship is already discovered, like it's kind of straightforward to write various type of codes, like to derive this, to implement this, right? This would be like one example. Like when we do this, you probably already noticed that we assume that the graph is already like a topological sorted. Then what we need to do is just create, like areas to memorize this result of the sub problems. We're going to initialize these areas to zeros at the beginnings. Like for the base cases, we have a node v minus 1. We just initialize this with 1. And then we are going to have a iteration over the longest, second largest node to the very first node, right? We're going to, after we are a loop over this, we're considering like, okay, we are going to find the maximum S for any outcoming edges from the node, from the node V, right? We're going to examine each of the outcoming edges and identify what will be the corresponding node of these outcoming edges from the node V, right? Then we check SW and see like where, if it is a larger one. And after this kind of loops, we just add one to this result of SV. I mean, that would finish the calculations. This would give us the result of the longest increase subproblems. All right. So far, are we all good about this? Do we have any questions? All right. Let's move on. So, like as I said before, this is crucial to define these subproblems. And previously, we just have a definition. Say, I'm going to calculate the longest path from index I, right? Actually, we can consider in an alternative direction. We can consider like maybe we can define our subproblems, like from the index 1 and any at index I. Right? I mean, this is also like alternative definitions, but we will also be able to derive this results. All right, let's just take this like examples, like apply into these areas, the same areas that we have covered. So just the areas with like 7 integers with 8, 3, 6, 6, 4, 5, 7, 7. Right. So now in these cases, like S4 is the longest path, the longest increase in subsequences from 1 to 2, or from 1 to 4. Right? I mean, we just highlighted in either like a black color or red colors. Right? I mean, all the remaining colors in grays are not considered. So we are going to finding the longest length of the increase, or of the length of the increase, longest increase subsequences, which is 4 in these cases. Right? We only have like 3 and 4. We're talking about S5. I mean, we will have we're talking about the longest increase in subsequences from index 1 to index 5. I mean, this would have a result of 3. All right. So after this is there, after we have defined this subproblem, we are going to derive the relationships. How we're going to solve the problem using like subproblems. And the very first thing we need to do is that we always start from the smallest problem, right? The smallest problem in this kind of definition would be S1. S1, like from the S1, we always have the longest path to be 0, so we immediately can derive the result, right? Remember, like S1 is what will be the longest path starting from node 1 and ending with node 1, right? There will be like no outcoming edges, so it just be 1, just be 0, okay? And then we're talking about how we're going to derive the result of Si. When talking about Si, we are going to loop over all the possible edges that from J. If there's the connect edges from J to I, and then we'll loop over all these edges. And with the node of Sg, we take the maximum value of Sg and take the and add 1 on top of this. This will be the result of the Si. All right. Do we have any questions about this kind of definitions? No? Okay. Again, this will be like the like code of this implementations. Remember, like this kind of definitions provide some advantage. It does not require we to have like a topological sorts. So we can directly have like create like a memory arrays. Like this will be like like as we have defined, we initialize with zeros. Then we just put the base cases, which is S0 equal to 1. All right. Now in these cases, we are going to have starting from the index from like a 1 until to the array's length. All right. For each of the items, we just find the maximum S for all the preceding nodes. Right. We're going to examine all the preceding elements in the sequence. So if AI is smaller than AI, then it means that if AI is bigger than AJ, right? I mean, we just check what would be the maximum values of our SJ. After that is there, we just add 1 values to the values of SI. That's it. That will be the result of the longest increasing subsequences. All right. So far, we have just talking about like 2 different definitions of the subproblems. You probably realize that it's very crucial to come up with a definition of the subproblems. You probably need to consider what will be the overlappings, and how to derive these results. You start with the simplest cases of the subproblems. You derive how you're going to solve this bigger problem using the existing like a result of smaller problems. Right? That will be the main ideas. And now, maybe you like we have finished the descriptions about the like the algorithm itself. We probably again we want to like have evaluations analysis of the running times, right? What will be the complexity? What will be the running time of these algorithms for like input sequences of name numbers? All right. So just take like 5 minutes of like a break here. We just resume talking about like the result of the answers to this question. All right. Okay, let's get started. So the result of these cases will be n squares, right? So if we consider why this n squared, maybe we can just have like a brief summary about the algorithms. So we have defined our like subproblems to be Si, which is the longest increasing numbers, increased sequences from the index from the areas of 1 to the index of I, right? So this would know like you immediately realize there will be like n like subproblems, and each of the subproblems I actually takes time over Y, right? We sum them together, you give us total result of n squared, right? Good. So this would be considered like, okay, we have a complexity of O n squared, like you probably can, this would be the questions you consider like how are you going to do this in a time of n log n, right? I mean, it's quite a challenge. It would be great if you can derive this, right? And there are some hints. You can use like a binary search to solve the subproblem faster, right? So now let's move on to our next questions. We have talking about, like so far we have talking about the basic ideas of dynamic programming. We also apply these ideas to solve like one simple examples, which is the longest increase in subsequences. Now let's move on to consider talking about another like a more complicated like a questions of examples, right? Which is like a price connection. So when talking about like a price connections, the input would be like a directed arrow, directed graph with like a V as the vertex and AE as edges, right? And you already noticed that the edge weights would be the price on the each edge, right? And this would be like a directed weighted edges. And so the output of the price collection algorithm would be you just have a path that's that's all this result along the path it would be the price. For example, we have like a path that we highlight in like blue colors. Then the outputs of the prices along that path would be like a summations of these like weights along the edges, right? This would be like together would be 7 plus 2 plus 1, so the result would be 10. And you probably also already considered this question, like what would be the maximum price we can get from this graph, right? There are different options. This is a kind of very interesting one. So like the options will be 1, 2, like a 3, and like 10, 50, and 70, and infinity, right? So the previous we already give you examples we have like a price of 10, right? So maybe you can figure out what would be the maximum prices here. This is very interesting. Let's see who can get correct. We probably also consider why it would be infinity option. Like we already have like a result of 10, right? I mean, this directly get rid of these options of 1 and 3. Can we really have infinity? Okay, actually the maximum price you can get actually is infinity. Why this is the case? Like turn out that there's like a cycle, right? I mean, if you we just highlight the cycles in red colors. You see, like if we move towards the ages, you start from age 7, then we will have like age 2, and then we have like areas like age 1 and -5, and then we have 3, +3 and -3, and the -4. Then we reach to the original code, right? Then we have just finished a cycle. The good news is like the weight of the cycle actually is positive, right? I mean, it is like it's 1. This would just give us like options like we can run infinite like loops along the cycle to give us the infinite prices, right? And the side problems would be for this like a price connection would be how could we determine if there's like a positive weight cycles in the graph? Any ideas or thoughts? It seems like once you identify this, you win, right? And you get infinity results. So I think this should not be a difficult one. So let's say like we can just check for like a positive weight cycles, we just negate the ages and then run like a Bellman form. I mean, this will give us the results to check whether these like a positive weight age cycles, right? So now we just have the introduction about the price connection. But again, we kind of want to like restrict this problem so that we can apply, like idea of dynamic programming to solve this, right? So the input of this would be a graph, and the age weight is just the prices on each of the ages. But right now we have like limitations, which means that you cannot run infinity long steps. You can only cross at most k ages, right? This will actually like have like restrictions, right? So that you probably don't have like infinity results or the infinity prices outside of this the problems, right? Maybe let's take some of the examples. So if the k equal to 1 means you can at most cross 1 ages. So the maximum result you can get is always 7. And again, if we have like, you can at most cross 2 ages, we increase it from 7 to 9. We just go through this like, ages, right? And then when the age is like a 3, we will have a 10, right? And these are the 3 ages with the like, continuous positive ages or weights. So if we are allowed to apply like at most 4 like steps, we still like keep like we just choose like a 3 steps. We just stop because like after we reach this node, if we take actual steps or take 1 ages, it will give us negative result. So this does not make sense for us to move actual ages, right? We keep doing this, right? If we increase the k until to the level of like a 70, remember, like we already showed that there's like a cycles, right? And the summation over the cycles would be 1. And if we're able to, allow to at most run like 70s, it turns out we are reaching the same result of 10. Means we are going to have like 10 loops of the cycles. It also gives us the results of 10, right? And then continue to increase the k to be set from 70 to 71, then we'll have the result of 70s, right? So these are just kind of the examples we have trying to get you familiar with the definition, like lazy, like price connections. To know that this kind of problem definitely will be like not shortest path problems. It's related with like longest path. It also have like a negative like wave cycles and positive wave cycles, right? And these are the kind of the understandings about the problem itself. So how we are going to solve this one? How we're going to solve these problems? The idea one would be, okay, let's transform this into like transform the graph into like a diagram, right? And we just make like k copies of every node. Why we want to do this? Maybe we can have like examples. Like if we have ages, or we have like a graph with 3 nodes, then we just make like 2 copies, or we just make 2 copies, and then like we will have like each of nodes twice. 3 times. And we are going to draw the ages, for example, we know that we will be the ages from V to W, right? Then we are going to draw the ages from V to W, all the ages, right? And you get the ideas how we're going to construct the ages. So, and if there's like another cycles, which means that we will have like ages from Z to W, we just cross this from ages to Z to W's, right? So by doing this, we will transform this like a graph G to a directed a cyclic graph, right? And after that is done, we will be able to just solve this longest path finding problem for each of the sources. And this would give us the kind of the results we want. But before we continue, maybe we can have like a basic evaluation about the running time of this ideal one. What will be like running time? There's several different options. We have like OE or OVE or KE. Maybe you can type your answers and let's see whether what's your results or what's your answers to these questions. Okay, let's see. Actually, the result is KVE. And also you can consider like the lab key, right? So the question after these descriptions, you probably want to ask yourself, do we really need to like run like a repeated V times to find this results? Do we really need to call this longest path like a V times? It turns out that this is really not necessary. Like this is the general like tricks or like formulations, right? We can just create like a super source code, a super source node, and directly connect it to every of the edges of every of the nodes. With like each of the directed edge would have a weight of 0. Then we just run this longest like a passes, starting from the super source node, right? And remember, like after we transform this graph, it will be like a KV node and a KV edges, and the like the running time of this longest path finding will be like a magnitude of KV plus KE, right? And this will give us the result. Now, maybe let's consider like how we are going to solve these problems using the ideas of dynamic programming. Again, when we're talking about using like ideas of dynamic programming, it's always important to see how you're going to define your subproblems, right? Now we define our subproblem to be like a like a PVK, right? PVK means it's like it takes the two parameters, which is V and K. The K is indicating that you're going to calculating the maximum price that you can collect starting from the like a node V, all right? K specifies you can exactly taking K steps. And this would be the definitions of the subproblem, right? We just have this like a PVK, and later you'll realize why this is like a reasonable like a definition, right? And before we dive deeper into like a relationships, like how to derive the subproblems, maybe let's consider like simplest case, right? What will be the result of the KV0? Means that you start from what will be the maximum price you can collect from starting from the node V, but just takes 0 steps. What will be the result? 0, right? You start from the V, the vertex V, just take the exactly 0 steps, you get the result of 0, right? So now we would have like a simplest case, which is like each of the result, if the K equal to 0, we just have like a V0 to be 0, right? That it would be one of the smallest problems. Now, we probably want to derive this like how we're going to solve the PVK using the subproblems, right? In fact, the PVK of the subproblem is like like we can consider like the maximum price. You can connect it from like the node V, but taking exactly the K steps. You can just take consider like a one step further, right? I mean, you know that you consider like what would be the nodes that are connected to this. What would be the like a neighborhood node connected to the vertex V, right? We just rename this all this neighbor node to be like a V1, V2, V3, etc. And for each of the subproblems of starting from V1 K minus 1, which means that this would be the result is the maximum price that you can connect it, starting from the vertex W1, but it taking exactly K minus 1 steps, right? And then we are just, what we want to do is we want to say like how we're going to derive the result of KVK, right? I mean, this is like we look over all the possible, like the like subproblems. We consider we just have like a PV1K minus 1 as the weight, the age of the weight from V to from V to W1, right? And this would be one of the possible options that the prices you can connect it start from like a V and run exactly K steps, right? After this kind of summation, these are one of the options, right? You start from vertex V, you take exactly K minus the K steps, because you can consider this procedure to be first take one step from the vertex V, from node V to node W1, and then continue to run K minus steps from the node W1, right? And remember the definition of PVK is the maximum prices you can connect it, starting from V, right? What we need to do is just we loop over all the possible passes, starting from node V across each possible neighborhood node, like W1, W2, W3, and just select the maximum, like the prices, right? That will be that is how we're going to solve this like a PVK using these subproblems. All right, are you all good about this? Okay. So maybe let's apply these ideas into some concrete examples. Let's consider like like already we take this node of in the red, take the node of V to be red. We already know that like a PV0 is 0, right? Now let's consider what will be the result of the PV1 starting from the red node, right? And from the red node, you will see like there will be just two like edges starting from the node. Just with this node, sorry, with these edges and these edges, right? These are the two neighborhood nodes that with like outcoming edges from the red nodes. Right. What we need to do is, like we know the result of these two nodes. Let's just name the A and B. We know this like a PA0, right? PA0 just 0, and PB0 will also be 0. And we just sum them to with the edges starting from the node from the red node to the A node and B node. Then we just take the maximum result. This will give us, like a result of 2. Right? This would be the PV1. Now let's talk about the PV2, right? PV2s, again, when we're talking about PV2, they are still like only we compare like what will be the possible result of these two nodes with the A node and B node with PV1, right? PA1 and PB1, right? So PA1, like this node, we just know like what will be the maximum price you can get starting from this specific node and take exactly one step. Right? By taking exactly one step, the maximum price you can get is just 1. Right? You should add these edges with 2. This will be the one possible like prices that you can connect it. Starting from node V, take twice steps. Right? And then we probably look at this node of node B. Like what would be PBV1, right? What would be PB1? PB1 is you're starting from the specific node B, and you only take, like one steps. What will be the maximum price you can collect it, right? And it seems like there's only one path. You have to take one step. You just give -5. I mean, this would be like a PB1 would be -5. We take the maximum. We take the weights from the node V to the B, which is -3, right? And then take the maximum between the two like a possible like a weights. Then we have the result of 3. Right? Again, we can have like a PV3, right? PV3 is like we're talking about, okay, we are going to derive what will be the edges of a node, what will be the PA2, right? PA2 means that you start from the node A, you take twice steps, right? If you take twice steps, what will be the maximum weight you can get? I mean, if you take twice, this would be a reasonable direction, right? This will be one direction, and the maximum weight you can get from the specific node of A right, would be -4. You plus this result of edges like connecting with the node V to A with 2, then it will be a result of -2. Another case, you remember there's always like a B node, right? This case, we need to calculate in like a B2, right? PB2. Which PB2 means that you start from node B, you take twice. You take twice steps, then the maximum rates you can get is -2, right? You just take these 2 steps. This will be -2. And you just add on top of this -3, then take the maximum, they will get the result of -2, right? I guess you get the idea as to why these are the definitions of subproblem, right? And in fact, you can look at this in the table views. like each of the items will be like the horizontal, the row axis would have a bunch of like 10 nodes. And the case represents a different type of like a steps you can take, right? I mean, each of this kind of have like a maps or like a matrix. And each items, if we have a definition, each item would be like the subproblem, right? And then we are able to like fill in this from the iteration one, and like then when we fill in the iteration one, we will have this result. Then utilize the dependencies, we will be able to gather, like the result of the second rows and keep doing this and keep doing this. And this would be the table views, how we're going to derive these problems, right? And this will be like implementations, and this will be the side of code. Again, all of this code is just trying to implement the same result we have just work out together, right? I mean, this is just like implementations of these ideas, right? How we are going to solve this PVK after we have definition of PVK, how we're going to solve them, how we're going to derive their relationship using the like subproblems, right? Look at the code together, then we'll have like like tables to memorize the subproblems. We're going to initialize this like tables, with zeros. Then we'll have like iterations from k to 1 to k to max, right? I mean, this we are going to solve each of the values of the keys, right? Then we'll have like second iterations, like from the second iteration would be here, right? From the vertex V1 to the vertex length. Every of the node, we just check, finds the maximum prices in the next steps. And, we check, like what would be the PW, just identify or represent the W as the, like a neighbor node of the V. And we're going to check like a PWK minus 1 plus this the age weights of VW, whether they will be like, what will be the maximum values of this one, right? I mean, just take that into the result of PVK. So after that is done, we just output the largest entries in the P. All right? Do you have any questions or? Okay, all good? Okay. So after this is we have we have two ideas. One was say we're going to transform this into a directed cyclic graph. Then we just solve this problem using dynamic programs. Okay. Now probably want to consider what would be the ideas, right? If we have this, we are trying to solve this lazy price connections. We just use the idea of dynamic programming. So we would have the definition of subproblems of PVK. And now let's talk about the total cost this time. Remember the PVK would be what would be the maximum price that you start from vertex V and take exactly the k steps, right? And you probably identify why we want to have this definition and take exactly k steps. We just force it to take k steps because we can decompose the k steps can be considered as edges between the nodes of V with the neighborhood node W, and plus the the subproblems, right? I mean of PWK minus 1. We just take the maximum value. This would give us the result. We are going to solve this, use the subproblems, right? And then you probably want to analyze this. Okay, what would be the total cost of this kind of ideas? There's two factors in the process. First, we need to identify how many subproblems exist in here, right? So the number of the subproblems would be KV, right? And then we will begin to analyze what would be the cost to solve each of the subproblems. So when we solve these subproblems, we just loop over all the V nodes neighborhood, right? And at the most, it will be V. So we can have estimation of the upper bound to be a KV squares, right? I mean, that would be one possible direction, all answers. However, if you look at these table views, you probably realize, okay, we kind of have a better bound, upper bound, right? Each of the items would be, each item in the table would be the subproblems, right? We're trying to finish this the result. We're just filling this items one by one, right? One row by one row. And this means that if you look at the total cost from the table point views, there will be how many rows? It will be k rows, right? We kind of calculating like what would be the maximum time step you can collect by taking exactly k steps. And if we, what will be the cost to solve each rows? The cost to solve each row will be exactly the E edges, right? And total result would be like KV, KE. Because like you're going to consider like each of the node, you need to consider like the incoming edges from the specific node to that outcoming, that neighborhood node, right? Which means each edges is calculated. Each edge will calculate once, and we're going to fill in the rows, right? And this would be the total result of KE. All right. So far, we have like applying our dynamic programming to solve like a second examples of the problems, which is like a price connections, right? So now let's move on. Let's talk about like another interesting and also a classic problems, which is called like a vertex cover on the tree. I don't think I have enough time to cover the next one, all pairs shortest paths. Let's just leave that on Wednesday. Let's see what would happen, right? So the vertex cover is a very classical definitions or classical problems. The input will be like undirected, unweighted graph, right? This is very good, simple. The output of the vertex cover would be, we want to have like a set of nodes where like each of the edges is adjacent to at least one node in C. That is like we are going to cover all the edges with a vertex, right? These are the definition of the vertex cover. Remember, in these cases, we have like a graph, like we are going to select a bunch of nodes that we highlight in the blue colors. After this kind of selection of the nodes, you will realize that each edge in the graph is kind of covered by the vertex in red colors. By say like covered by the vertex in the red color means that every edge is adjacent to at least one node in blue colors. Right? You can look at all the possible chances, like each of the edges is connected by the blue colors nodes, right? You can check. So this is the called like vertex cover. Cover the graph edges, use a vertex, the set of vertex, right? Turn out that like we are always really interested in find the minimum vertex covers. Unfortunately, this is kind of an NP-complete problems, which means that like there's no polynomial like a time algorithm to solve this. The best that we can do, I think, is just to have like a two approximations by matchings. We don't know whether we can do better than now, up to now yet. So these are not the problem that we want to tackle like in these classes or in these lectures. Instead, we will kind of have like a simplifications. Let's consider like a vertex covers on the tree, right? It is same type of problem. You want to cover the trees, use a set of vertex, right? So the input will be undirected, unweighted trees, right? By trees, we also provide you another like information, which is the root of the trees, right? Again, the output would be you want to have like a set of like a vertex covers that will cover all the edges, which means that every edge in the trees it will be adjacent to at least one of the nodes that is painted in color or highlighted in blue colors, all right? And we want you to output what would be the minimum vertex covers, what will be the size of the minimum vertex covers. For example, in these cases, we can have like an example shown on the left-hand side. We will have like trees with 4 nodes, right? We have 1 edges. We just use the root node as the vertex covers. You will see that, okay, all the edges in the tree is covered by the node in the blue colors, right? We have now, let's look at another relatively complicated like trees showing on the right-hand side, right? The size of the minimum vertex cover on the trees showing on the right-hand side would be 2, because we can just cover the trees using 2 red colors, 2 blue nodes. You see, after we identify these 2 blue nodes, every edge in the tree is covered by the vertices in blue colors. All right. So, okay, these are kind of like a brief introductions about the problem itself. You're probably starting to consider, okay, how we are going to leverage the dynamic programming to solve this. All right. And before you consider that, you're probably already thinking about, okay, what are the subproblems, right? And like you probably already realized identify the subproblem is very crucial. Once you identify the problem, you could always solve the immediate get the result of the smallest or simplest subproblems. You kind of build this, solve this bigger problem, use the results of the subproblem. Right? That will be the general procedures. So what will be the subproblems here? For the trees, itself, like a subproblem is already kind of, you already have like a substructures, right? I mean, when we're talking about the trees, we're already talking about like a subtrees that's rooted at a specific node, right? This kind of already have this like a subproblem structures. But you probably want to consider, is this sufficient enough to identify the problems? For example, if we consider like a subtrees here, while we can simply utilize like a subtrees, like rooted at this node, let's say like this will be node A. What is sufficient to describe the subproblem? I mean, we can describe the trees, subtrees starting rooted at node A, right? But this really does not tell us, okay, what will be the like a vertex cover. It's just talking about how you're going to divide the trees into sequences of small trees or subtrees. And then you will realize this is crucial for us to identify whether the root of the subtree is in the vertex set or not, right? You need to have some information tell me, okay, in this subtrees, please tell me whether this node is in the vertex cover or not, because it will be significantly different, right? Let's consider the cases. So we just have like a specific samples, like samples with a V0 and a V1 to talking about the two situations, right? We just have all of them. All these two cases have the same trees, which is rooted as node V, right? If we consider like SV0, the definition of SV0 is the size of the vertex cover in the subtree that's like rooted as the node V. However, in these cases, V is not covered, right? When V is not covered, we will need to use like the two nodes as the leaves to cover these two edges, right? But the most important thing you need to notice is if V is not covered, you probably also need to pay attention like how are you going to cover these edges, right? When you divide this problem into like a subtrees, probably want to consider like what's the situation of these edges. And then we'll have like another situation as we call like SV1. SV1 means it's the same subtrees rooted at node V, but the V is covered, right? Once V is covered in these situations, the size of the vertex cover is 1. The good news about this is, okay, we know that these are already being covered, which means that we really do not need to care about, we do not need to pay a specific situation to care about whether this node is covered in the vertex, not covered in the vertex. But in these specific cases, if we look at these edges, we have already know that the node V is not in the vertex cover, right? What does it mean? It means that we have to paint this node to be blue, right? We have to paint this to be blue, so that the edge from the root node to this node V is covered, right? I mean, these are kind of significant differences. That's why when we're talking about the subtrees rooted at specific node, we always need to have actual information tell us, okay, whether the node V is covered or not covered, right? These are the situations that we need to consider, right? Okay. Again, so turn out that these kind of definitions are also like a subproblems. Like we will have like subsequences of V, each of the V. We just say like, okay, what will be we can draw like a subtrees rooted as the specific node. Then we'll have a problem saying like, what will be the size of the vertex cover if the V is not covered? We just put the as V0. If it is covered, we just put as V1, right? I mean, turn out this would be the definition of the subproblems in this vertex cover on the tree problems. Now you probably want to consider like how many subproblems do we have here? Right? So this will have like we can have like how many different nodes we could have. Each of the nodes in the tree could be induced into like they could be taken to the first parameter of the SV0 and SV1, right? So I mean together, for each of the nodes. However, for each of the nodes, we have two situations: whether the node is covered in the vertex set or is not covered in the vertex set, right? So together we would have two V's. So this would be the result. So we have two V subproblems. And then you probably want to realize that, okay, this is the definition of subproblem. You probably want to consider what were the base cases. What would be the simplest cases in these subproblems? The simplest problem would be only the leaf, right? The simplest tree, the simplest subtree rooted at a specific node would be the leaf node. And if then we can derive like, okay, as leaf 0, which means that, okay, the vertex, whether the vertex is covered by we have like a root, like a leaf node as a subtree, as is rooted as itself, and this node or subtree is not covered inside of vertex cover, right? I mean, then as leaf 0 would be 0. Otherwise, like we have just identify the specific node. This would be the cases of leaf as 1, right? We're going to cover this like a subtrees with with this specific node, put it in the vertex cover. So the F leaf 1 would just be 1, right? I mean, these are the simplest subproblem, right? I mean, you can immediately get the results. I guess next thing you're starting to consider would be, okay, how we're going to solve the problems by building the subproblems, right? So how we're going to calculate the SV0s. Let's consider this. If we do not cover, how about this? Let's consider how we're going to cover SV0s. If this means that we will consider the size of the vertexes starting of the subtree, starting or rooted at node V. But the node V is not covered, right? Let's consider like these cases. So if the root V is not covered, for example, these cases. If root V itself is not covered, which means that we need to cover all the V's child, right? If this node itself, this node is not, this node is like that, we need to consider all the child. All the child of this child should be like covered, right? And then the result would be SV0 would be, like we identify the V's neighborhoods to be like a W1, W2, W3, etc. Then the SV0 would be, like the sizes of SW1, SW2, SW11, SW21, and SW31. We just sum them all this SW, all the root nodes with like a node 1 with 1 to be the result. Okay, we just summarize all the possible cases because we consider like this will be the root, this would be the root, and this would be the root, right? So SV0 would be summations of the 3 output. It's like a SW1, 1, SW2, 1, SW2, 1, SW3, 1, right? This would be like a relationship of like SV0, right? I mean, remember the key part is like if the node itself is not covered, then all these child need to be covered, right? Otherwise, the edges from the node to its child is not covered by the vertex. Now let's consider like SV1. As V1 means this node itself is already covered, right? Then if it itself is not covered, then we probably need to consider like it is okay that we does not really have any restrictions that whether we should color the child to be like a node or like in the blue colors, not in blue color. We can either cover or not cover this child, right? Then like we will leave us two choices, right? I mean, whether we can cover it with like let's token this as W1, we have W2 and W3. Then there are two choices. We can all either like put it in like a 0 or put it like in the SW11 as W10. Right? We just take the minimum value of this, we just name it W1, W and W3. Then the whole result of as V1 would just be composed into like we need to add a 1 on top of this because the node V is already covered, right? Then we just the summation over W1, W2, W3. And W1, W small w, W1, W2, W3, just the like vertexes or the neighborhood of the node V, right? And this finished the result of this. Like we are able to derive this, like how we are going to calculate it as V0 and then as V1. All right. Turn out I don't have enough time to go through. So we will just pause here. And like we have in this vertex cover problem, we just have an introduction about the problem itself. What is the problem? What will be the input? What will be the output? And the most important part is how we're going to define the subproblems. And what would be the base case of the subproblems and how we are going to solve this problem using the subproblems we have defined. Okay? And we have just gone through this. I guess you can expect it that we are going to have like a detailed analysis of like complexities, how good these are, what's the time cost of these problems, right? So we just resume talking about the topics on Wednesday, right? Okay, I would like to end this here. So I'll see you on Wednesday.